Hello and welcome to lecture number 19. So in the last couple of classes, we've been looking at experiments using very simple robotic systems that have been basically made in the labs here itself. And the objective of that was that how we can make very simple robots and do experiments to understand the basics of robotics like forward kinematics, inverse kinematics, how to move a mobile robot or a serial arm or a parallel arm. So that gives us a very good experience of understanding the kinematics of such systems. Okay, and they are simple, so you can make them by using very cheap components like servo motors, which can be bought very cheaply and very easily available in the market. And we are controlling them using the Arduino microcontroller, which is also available today in the market. Okay, so the objective was that to understand forward kinematics, inverse kinematics, we used very simple mechanisms which you can make by yourself. Now let's move on from there. And today we'll look at industrial robotic systems. Now, industrial robots, of course, are more complicated in the sense that they are not actuated by simple servo motors, but they have brushless DC servos, and they have very complex control algorithms which are controlling them. For example, they could be having feed-forward control systems which are controlling the industrial robotic arms. Okay, so today we have two robots, industrial robots. One is a collaborative robot, which is called Swaya. Now, the Swaya robot is an Indian robot. It is manufactured in India, and it's a collaborative robot. Now, what does that mean is that it is safe in terms of application or where the robot has to work with a human. For example, if the robot were to hit a human, okay, suppose the robot is moving and you put your arm there or you come in between, it will hit you, but then it will immediately stop. So that it understands that it has hit something somewhere and it will immediately stop or it will go backwards. Okay, that is one. The second is that you can program such robots by holding and moving it. So you can hold the link of the robot and move it around. Suppose I want to go and pick up an object from the table. So what I can do is I can take the robot, catch the end effector of the robot and move it to the object and grasp the object, then move it up and then move it wherever you want. And when you're moving, you can record the various positions of the trajectory and you can play back. So this is a very simple way of programming a robot, which you cannot do with other industrial robots. Now, the Swaya robot is a collaborative robot. It's also an industrial robot, and this is the most advanced generation of robots today, because in industrial applications of the future, it is expected that robots and humans will work together. In that case, robots have to be safe, and that is where this question of safety collaboration comes into picture. Now, if you're wondering how does the robot sense, well, there is no force torque sensor in the wrist of this robot, but it basically monitors the motor currents. So if the robot were to hit something, it immediately knows by observing the motor current that the motor current has gone up, means the force has suddenly increased somewhere. Okay, that's how it understands that it has made contact somewhere. Now, in this experiment, we'll show you how to program the Swaya robot. It's a very simple programming method where you can use a GUI, and there are blocks in the GUI. For example, move, grasp, okay, delay. So you can simply take these blocks and teach the program and give the points. Now, how do you teach the points? Again, there is a joystick. In the joystick, the joystick is also on the computer. You can see it on the computer screen, where there are toggle keys, and you can simply move the various joints. So there are 6 joints, and when you move the toggle keys of joint number 1, for example, the joint number 1 of the robot will move. So you can move these joints using the computer mouse, and then what will happen is the actual robot will move, and you can record the positions there. Okay, and then you can play back. So that's one way. The other way is you physically catch the robot and you move it and take it wherever you want it. Okay, and then you can play back the positions. So that is about the Swaya collaborative robot. Now, the second robot that we'll be seeing is the industrial robot, the Puma robot. Now, the Puma robot is one of the earliest robots that was made in the US about 1960s, okay, by the Unimation company. And almost all the textbooks in robotics that you see, they would have the example for forward kinematics and inverse kinematics, giving the example of the Puma robot, because that was a very, very standard robot even today in terms of the structure, in terms of the kinematics. So the Puma robot is an industrial robot. It is not a collaborative robot, so you cannot catch it and move it around. Okay, and it's a very old robot, so the programming of that is also has to be done by means of the VAL2 programming language. Now, VAL2 language, as I explained in one of the couple of classes back, is a basic language kind of a programming language where you define one line, you define a line number, then there is a line, then there's a line number, there's a line, and the compiler executes line by line. Okay, so the robot has to move from one point to another point. For example, we simply write move p1, then we have to define the point p1. Okay, so we write the program in val language, which I'll explain how we write the language. Then I'm going to enter the language in the console of the controller, and then I will execute it and the robot will follow that. Now, how do you teach points? Now, in this case also you have a teach pendant, and when you move the toggle keys on the teach pendant, each toggle key corresponds to a joint. What will happen is that the corresponding joint is going to move. So if I want to take it to some location, I simply use the teach pendant, take it there and teach that point. Okay, that's how we teach. In the case of the Swaya robot, of course, you were able to teach it both by moving it manually and by using a teach pendant. In the case of the Puma robot, we have to teach it by using the val language. Okay, so today we'll look at the two robots, Swaya and the Puma robot, and both of these are industrial robots. Okay, this is the manual of this experiment today that we are going to do. And as I was explaining, there are two robots there. One is the Puma 560 and the Swaya SR L6. This is the model number of the robot. And these are the two robots that we are going to see today. Okay. Now, what is the objective of today's class? The objective of today's class is, number one, to study the forward and the inverse kinematics of the Puma robot and the Swaya robot, and then look at the commands for using the Swaya and looking at the commands for operating the Swaya and the Puma robot. Okay, so this is today's task. So the first thing that we will do is learn the basic commands for Puma. Well, that's not the first thing. So first we'll look at the Swaya robot, then we'll look at the Puma robot. Okay. Now, before we proceed, there is a little homework for you. That is, you have to supposed to write down the DH parameters of the Swaya and the Puma robot. Okay. Now we know that before writing the DH parameter, we basically have to assign access. After you assign access, then you are supposed to make the DH parameter table, and from the DH parameter table, then you have to supposed to do the forward kinematics equations. Okay, so the left one here is the Swaya 560 robot, and the left one is the Puma robot. Sorry, it's written here is the Puma robot, and the one on the right is the Swaya robot, which is written here. That's the Swaya SR L6 robot. Structurally, you can see that this is more curved in terms of the shape, and in this case, this is the Puma robot, which is a very standard robot used by for teaching robotics in almost all textbooks. Now, this is the structure of the Puma robot, which I had explained in class. So the axis system is also given there. It has 6 axes. This is the first axis. That is my Z0. That's my Z0 and Z1. This is the second axis. Okay. There's the third axis. This is the fourth axis. There's the fifth axis, and this is again the sixth axis. So Z1, Z2, Z2, Z3. This is Z4, this is Z5, and that is Z6 again. Now, correspondingly, you can put the x-axis and write the DH parameter table. Okay, so you can take this as a homework and do the DH and write down the axis for this robot. And after you have made the axis for this robot, what you can do is you can fill in the DH parameter table, which is shown here. So this is my DH parameter table for the Puma robot. Okay, so it is A, alpha, D, and theta, and there are 6 degrees of freedom. It has 6 joints which are given here. Okay, so this is a good exercise for you to understand how the robot is actually, how the forward kinematics of this robot is done. Okay, so this is the Puma robot. It has been taught in class also. Okay, now something to note here is that the last 3 axes intersect at the point here. So we have our z-axis here. So this is my Z4, that's my Z5, and that's my Z6 again. Z4, Z5, and Z6. They all intersect at that point. Okay. Now, if you look at the Swaya robot, this is the Swaya robot. Okay, the one on the right here. Now, the structure is a little different in the sense that the first axis is here. The second axis is there. So that's my Z0, this is my Z1, this is my Z0, Z1, this is my Z2, this is my Z3. Then that's my Z4. This is Z4. This is the fourth axis, the roll which we call the roll Z4. That's my Z5, and this is Z6 again. So the structurally it is a little different. For example, the roll in the Puma robot is at the wrist, okay, whereas the roll in the Swaya robot is at the elbow. So this is my shoulder, this is my waist. In terms of definitions, we say this is my waist, that's my shoulder, that's elbow, and roll, pitch, and yaw are there. So in this case, this is my base, which is my waist, this is my shoulder, this is my elbow. The roll is again at the elbow, and this is a pitch and a yaw there. So the structure is a little different, so the kinematics is a little different. It's a little tricky to do kinematics here. In fact, the last three axes are not intersecting. So you may need to do numerical computation there. Okay, so you can also write down the DH parameter table for this robot, which is a little bit more tricky, and then try and do the forward kinematics. Okay, so we'll be looking at these two robots today. Okay, this is the Swaya collaborative robot. So this is a collaborative robot, which means that it has safety features to interact with humans and collaborate with humans. So as we go along, we'll see what are the various features of this robot. Now, first we see that this has 6 degrees of freedom, and it can be programmed either by using the teach pendant, which is shown now, which is down there. So that is the teach pendant, and this is the basic PC-based mode. So this is the computer, the PC, where also we can program it in different modes. Okay, so first what we'll do is, this is the mode where we can jog the different joints. So you can see that the various joints are drawn there. Okay, so 1, 2, 3, 4, 5, 6 joints are there, and by moving the cursor you can move the corresponding joint. This is manually. Okay, and when you move, you can see on the left hand side, that is on this side here on the screen, the robot is also going to move. Okay, so there is a robot simulation which is here, which moves. This is the teach pendant, which we can manually change the various joints, and then you can see this is the real robot which is here. So when we are going to move on the computer screen, the simulation will move and the actual robot is going to move. Okay, so these are the 6 joints in the robot. The first joint is this one, which is the base joint, which is a vertical joint. So let's move the first joint. So you can see that the first joint is moving, the vertical axis is upward, and this is the first vertical axis of the robot. Okay, now the second joint is, you can see that this is the second joint. Okay, so the arm is going to go up and down. So that is the second joint. So you can see that the arm is moving, or maybe I'll see it from the side. Okay, so that is the second joint. This is the second joint. Okay, so the arm is moving about the axis here. Oh, this is a large robot, so it goes out of frame. So this is the axis which is coming outside from there. Okay, now it is going up again. So this is the second joint. So the first joint was this one, vertical. Second joint is horizontal, which is called the shoulder. The third joint is the elbow joint, which is this one. Okay, so maybe we can move the third joint, which is the elbow joint. And the elbow is going up now. That is the elbow joint which is moving up. Now you can see that as it is being moved in the computer screen, the simulation is also moving. So maybe I'll bring it closer. So the simulation is also moving. So in the real world, in the simulated world, there is a complete correspondence 1:1, and as it is moving, the joint is moving in the simulation and also in the real robot. So this was joint number 3, that is the elbow joint. Now this is the joint number 4, which is called the roll axis, which is joint number 4. So the joint is a vertical axis, and this is the vertical axis about which it is rotating. Okay, in this particular configuration. So on the side, if we see, this is the joint is here. Okay, that's the vertical axis of the joint. So this is the roll axis. In the case of the Puma robot or the human arm, the roll axis comes at the wrist. Okay, in the case of the human arm, it is at the elbow, but in the Puma robot, which we'll see, that comes in the elbow of the robot. In the wrist of the robot. Whereas in this robot, it is coming at the elbow, which is very similar to the human roll. Okay, so this is the third joint. So again, joint number 1, joint number 2, joint number 3. This is joint number 4. Okay. Now joint number 5 is this one. That is joint number 5, which is a horizontal joint. So when it is moving, you can see that the arm is coming, not the arm, the wrist is coming down. Okay, the wrist is coming down. Okay, so this is my axis, the 5th axis. So this is the 5th axis which is moving. That is this one. Okay. Now, the sixth axis is the roll, which is this one. This is my axis, which is vertically out, coming out from the gripper. So it's vertical. This is my vertical axis. Okay. So this is the vertical axis, which is rotating now. Maybe you can see it closer. Okay. So that is a rotation about the vertical axis. Sorry, this is not the vertical axis, the sixth axis, I mean. Yeah, this axis is the sixth axis. So that is the sixth axis. Okay, so that gives us the sixth axis, axis number 1, axis number 2, axis number 3, axis number 4, axis number 5, and our axis number 6, which is here at the back. Okay, that. Now you can see that the structure of the robot is little different from that of the Puma robot, in the sense that it has a very curvilinear structure. Okay, so it is curved and the roll axis is coming here. So if you look at the joints, they are curved. Okay. Okay, so we have seen the basic how to move the various joints using the teach pendant, and the simulation of the robot that is correspondingly, there is a 1:1 match with the actual robot. Okay, so this so we have 6 axes plus the gripper, so we can make the gripper on and off. So this is the gripper of the end effector in this case, which is a gripper, and this is a pneumatic. This is not pneumatic. This is an electrical gripper, and the gripper can go on and off. So the gripper is in open condition now, and now it is in closed condition. Okay, it doesn't come close more than that. It's not required. Okay. So that's the open and close motion of the gripper. Okay. So we explained this the 6 degrees of freedom of the robot and the gripper. Okay, open close of the gripper. Now what we can do is, let us look at writing a very simple program. For example, if I want to move the robot to some position, so the robot has come back to its original home position now. Now suppose I want to write a very simple program to move the robot from some point in space. Say for example in this point in space, I want to bring the robot. So what I'll do is manually, we can bring the robot to this point. Okay, and from here maybe I want the robot to go here. So I'm going to store these 2 points in the robot space, and then the robot will operate between these 2 points, or will move between these 2 points. So to do that, what we do is we write a program. As it is shown, it is very, very easy way of writing. So we can, this is a GUI basically given by the robot manufacturer. So unlike in the VAL language program where we have to write the program, here we can pick and place different positions. So this, we are picking a particular position and saying that, you can see we pick the position by going back to the joystick and move the various points. When I move here, you can see that the robot is also moving. So I choose a particular location, let's say by moving the various joints manually. Say for example, I want to bring it to this point here, okay, where my stick is, and okay, maybe at this point is 1 point. So what we have seen is we are teaching it manually to come to this point. So let me go somewhere else and show. So this is the point where we have just brought it manually now. This is completely manually being brought here. So this is 1 point, and I say that in the program, this is point number 1, okay, where it is where it has been taught. Okay, so okay, that's the point number 1. Okay. Next, what we can do is we can choose the move command. Okay, so we are going to move it to another position, which is, I want to bring it to another position now. So for the second position, what we do, again we use the manual mode by changing the various joints. Okay, I'm moving the robot, so the robot is moving to some other point now. This is completely manual. Okay. Okay, so in the program you can see that we have added point number 1. So if you look at the program carefully, it says start, then there is position 1 where it has been, you can look at joint 1, joint 2, joint 3, joint 4, the angles are correspondingly given there. Then it's going to join the second joint, the second position. So position 1, and below that is position 2. Again it gives the joint angles, joint 1, joint 2, joint 3, joint 4. And now what we can do is we can play this program. So it is going to play the program between these 2 points. Okay, so what we can do is move the robot between these 2 points. Okay. So these are the 2 points which we taught manually, very simply by choosing these 2 points and then writing the program. Now this is a GUI, so it's very easy. You just pick up the position commands, put it in there, and manually teach it. Unlike in VAL language, we'll have to actually write the program ourselves, okay, and teach the points. Here it is much easier. So we taught it the 2 points, and the robot is moving in between the 2 points now. Okay, so this is the simplest way of teaching program, by manually teaching the points and then moving it from one point to another point and repeating it. So this is probably the simplest way you can get in robot programming. Now what we can do is we can add other features. For example, we want the robot to go and wait at some point. Okay, so we have added another wait function there. So you can see the wait for time 1 second. Maybe you can make it 1 second is very quick, so maybe 10 seconds. Or 10 seconds, maybe 5 seconds. Yeah. Okay. So we have added one more block which says that wait at position number 2 and then for 5 seconds. Okay. So you can see that now what we are doing in the case of when we run the program, it moves from point 1 to point 2 and waits there. So what it is doing is it's waiting at each of the points for 5 seconds. Okay, so this is similar to the delay that we put in the VAL program. So this is the simplest way of writing a program where you can choose various blocks and arrange them in a serial way, the way you want the robot to move, and the robot will exactly follow the same program. Okay, or the robot will execute the same motion. Okay, so next let's look at the next part, that is, now suppose we want to pick up an object. We can say that an object, you can see there are 2 tools in front. So there is one let's say table or a stool kept in there, and this is another one kept in here on this side, and there is an object which is kept on that, a rectangular block. Well, it's not rectangular, it's 5 sides, so it's a pentagonal block which has been kept there. So what we can do is, from the start point of the robot, we can actually manually take the robot to this point, okay, and teach it what is the position and orientation of this part which is kept there, okay, and then close the gripper, pick it up, and then maybe go and put it on this thing here. Again, teach it the position and orientation of the point where we are supposed to keep, and then we can keep it at that point. Okay, so what you found is that it picked up the part. So the program has been written simply by teaching it the various points. Now let's play the program again and have a look. Okay, so maybe you can play back the program again, put the part in here. Okay, so this is a very simple way of programming a robot. Okay. Now, any other program is there for automatic motion? And when the robot is moving, you can see in the simulation that exactly it was doing exactly the same thing. Okay, so it is like what we call by in terms of a digital twin sometimes, that whatever the actual robot is doing, this robot is also doing the same. So you can see what it is doing there. Okay. Okay, you can run some of the program. This is another program which has been written earlier to move from some position to some other position. So you can see it in different directions. This is showing the covering of the whole work volume, or the full work volume of the robot. So it has a pretty large work volume, almost 1.5 meters. Okay.
Safety mode is on.
So that is something to show about the safety mode, that if it goes and hits something, it immediately stops. Okay. Okay. So let's look at. So that is one of the reasons why it's called a collaborative robot, in the sense that it can collaborate with a human. So in terms of safety, it can sense the force being applied. How does it sense the force being applied? It basically measures the motor currents. Okay. So if it hits something, immediately the motor current goes up, and it understands that an extra force has been applied, and based on that, it will immediately stop. Okay. Okay. So the next part that we have is, this is a collaborative robot. So we are able to program it even by catching and moving it. So you can actually catch the. So there is a mode. So we just change the mode of the robot. And by changing the mode of the robot, basically, so we can see that these are different modes of the robot. So we're going to change the mode of the robot, and then we can simply move it by hand. So you can see that she is just simply catching the robot and moving it. Now this cannot be done for an industrial robot. Okay, this can only be done for collaborative robots. So he can actually hold the robot and take it wherever wherever you want to take it. For example, in the previous case, we had the case where we wanted to pick up an object. So we can put the object and take it wherever we want to take it, and record the particular position. Then we can open and close the gripper. Okay, so this is a position where we can simply take the robot, program it. Okay, so he's straightening it. Okay, so suppose we have straightened it there, and we are saying that no, it is still not straight. No, keep it straight. Okay. So that is the point that is being taught, right? So that point is being taught. Okay, so it has actually learned this point. Okay, so that is the point that it has learned, just exactly the same way we were programming it. So this is the point where it has learned this point. So it says position, save location. It has joint 1, joint 2, joint 3. What are the corresponding angles? And you can see in the simulation also where the location of the robot is. And if you look at the robot, actually it is there. So this is something like a digital twin also, where whatever the robot is doing is getting simulated there. Now we can look closely at the hand. So that is where the hand of the robot is. Okay. Okay, so now we can take it up and take it to some other position. Now this is basically the reason why it's called a collaborative robot. So it's collaborating with the person in doing the particular task. So it has to pick up from there and keep it here. Okay. So that position has again been taught. So that's why position 2, which has been taught there. Okay, so the various joint angles from joint 1 to joint 6 are noted there. Okay. So we can also program for the gripper opening and the gripper closing. Now this is the primary reason why this robot is called a collaborative robot, because unlike an industrial robot, it can collaborate with humans in the sense that if it hits somebody, it is safe, and it can sense the force and stop. And the other is the moment you can program it the way it was shown very simply, that we can program it by simply catching it and moving it around. And writing the program is also pretty easy in the sense that you just have to pick up the various points and automatically it picks up, it can generate the program by itself. Okay, so we don't have to write the full VAL language code like we'll have to do for the Puma robot. So that's the code that is there. Okay. So it has gone to the start position. Now when we execute the program, it is supposed to go to these 2 positions. Oh, the positioning accuracy was not correct. Okay, it did not go from the top position. Maybe we should teach it the top position first and then go down. So when picking up an object, you have to go from top. So we have to teach it such that it goes on top first, okay, and then goes down straight. Otherwise this problem will come. This is something I had explained, that when you pick up an object, you have to go from the top down, go down, and when you are coming up also, you should come up straight. Otherwise this problem can come up. This position is moved also, no?
Yes, sir.
So take it down again and catch it.
So it's 3-4 points right and depending on.
Okay. So this is one point.
Yes, sir.
The second point is catch this one,
Yes, sir.
or take it down. Take it down. It has to go down straight. Yeah. Okay. That's the second point. So this is on top of the object, huh?
Yes.
Okay, then from here it has to go down straight.
Yes.
No, it has to go down straight, don't exactly straight. If you take an angle, it will hit again. So that's the second position where it's supposed to go and catch the object, and then it has to go up straight. Next, after catching it, it should go up straight. No, it should go up here only, straight here.
वो सब कॉपी कर देंगे.
And while dropping also, it should go on top and then go down straight. Okay, so we are recording that position that is supposed to drop it, not drop, but keep at that point, just on top of the point. And then we have to bring it down and keep it. So what you can see is that even very, very small errors, if it is there, because the joints are unlocked now. So some of the experiments which we had done, the joints were also unlocked, which means that it is free because it's in gravity mode. So the gravity pulls it down, so that fine positioning is difficult, in the sense that the moment, because it's completely free, the joints are free. So if you just leave it, the joints will start moving because of gravity. Okay. So the program is being written in which we have one point, then we go and catch it, then we take it up. So you can see that it's easy, you just move the various, you just move the various blocks around, and then the program is automatically generated for it. Okay. So this is much easier than writing the VAL language program in the Puma robot, which you'll be seeing shortly. So you can play it once and see. Okay, so it was able to pick up from here and keep it there. Okay. Puma robot. So this is the 6-axis Puma robot, and this is the teach pendant. You can see that this is a pretty old teach pendant in which these are the various. So this is the Puma robot, and this is the teach pendant of the Puma robot, in which we have 6 axes. So these are the 6 axes which are marked here: 1, 2, 3, 4, 5, 6. And these are the various modes. We say this is the joint mode, where you can operate in the joint mode. So if I press this, it goes into joint mode. Then there is world mode, tool mode, then computer mode. And for example, if I press this, it goes into the computer mode. So I can move each of the joints by toggling these toggle keys. So if I press one of the keys on this side, the robot moves. Okay. So first joint of the robot Puma is 6 degrees of freedom. So that is the first degree of freedom, which is called the waist axis. It is similar to our waist. Now that degree of freedom is a vertical degree of freedom. Okay, so it's a vertical axis, and that is called the waist axis. So the second axis, so this is my waist axis. The second axis is the shoulder axis, that is the shoulder up and the shoulder down. This is very similar to the human shoulder axis. So shoulder up and shoulder down. Then the third axis is the elbow axis. So this is my elbow up and elbow down. Okay, so this is the elbow up and elbow down configuration. And so we have the waist, the shoulder, the elbow, and then we have the wrist axis, which is my roll axis, which is my wrist roll. Now that is at the wrist, you can see. This is the pitch axis of the gripper, and this is the yaw axis of the gripper. Okay, so the roll, pitch, and the yaw are at the same point. And this is something we have studied in kinematics, that if their 3 axes are not in the same point, then you cannot have the inverse kinematic solution. Okay. So unlike the other Swire robot which we saw, what we see here is that the structurally it is different, in the sense that the waist axis is the shoulder axis and the elbow axis are distinct. Okay, they are not curved; they are on a plane, and the roll, pitch, and the yaw axis are at a point. Okay, they are all at the wrist. Okay, so this is the 6 degree of freedom Puma robot, one of the earliest robots that was made. Now suppose we want to write a valve program. So I'll write a valve. I'll draw a valve program here. Suppose we have an object, and suppose an object is kept on the table, and I want to pick up the object. So this is my object which I've kept there. And I want to pick up this object. So this object has some coordinate. Let's call this point P3. Okay. Now the robot could have been anywhere. So what we'll do is I will bring the robot here first to a point P1. Then I'll bring the robot to the point P2, which is above the object. And then I will use the approach command and position the robot somewhere here like this. Okay. So this is basically called approach. Approach the point P3 and keep a distance of 150. So what it means is that it will keep a distance of 150 from this point P3. So this is my point P3. Okay. And after catching it, I will again depart. Depart means going backward like this after catching it. So what we have seen in class also, I explained that when we are talking about robot programming, before catching an object, the gripper has to be positioned on top of the object. Then it opens the gripper, goes down, catches it, and then goes up again. So this up-down motion here is always in a straight line. Otherwise, there is a chance of hitting the object or hitting something else. Now, after it catches the object, so what was the plan? The plan was first it will come to point P1, then it will go to point P2, then it will approach and go to and keep a distance of 150 on top of the point P3. Then it will go down, okay, and then catch the object. That means close the gripper, and then go back upwards, and which is called depart. It will go back to the point P2, and then maybe it will go to some other point P3, okay, and maybe open the gripper, drop it there, maybe we drop the object there, okay, and then from P3 is already there, so down to P4, and then from this point we will go back to P1 again. So that's the cycle of what we want to do. So first what we want to do is we want the robot to go to the point P1,
then go to the point P2, then approach the point P3 and keep a distance of 150, means it will go and stand on top of the point P3, and then it will open the gripper, go down, catch it, then go up, which is called depart, it will go up straight again to the point, to this point, and then from here it will go to P4, open the gripper, drop it there, and then go to the point P1. So that's the cycle. So we'll write a program in VAL language. Let me call the program demo. Okay. Let me call it demo 1, and we'll write in VAL 2. That's the language I will use. Now in the other robot, the Swire robot, the programming is easy in the sense that we take blocks and we just arrange it, and automatically the program is generated. But here, as I explained in class earlier, that we're using VAL 2, which means that we have to write the program ourselves. Okay. So let me write the program. So first is the program name, then there is a line number, so let me say line number 10, or line number 1, 2, 3, 4, let me say 1, 2, 3, 4. Okay. So the first one is move to the point P1, so move to the point P1. Okay. Then number 2 is move to the point P2. Okay. So I'm following exactly what I've drawn here. The number 3 is approach the point P3 and keep a distance of 150. Okay. Then it is open eye, that means open immediately, which is a closed loop command. Then number 5 is moves. And notice that it's an S command, which means that it should move straight, moves to the point P3, and then we say it should close eye, close the gripper, close immediate. Then 7 is depart. So depart 150 means it will go up by 150 again. Then number 8 is move to the point P4. Then I can say it is open eye. That means drop the part there, and number 10 is move to the point P1 back to the point P1 again, and then number 11 is I can end the program. Okay, so this is the program that we have written in VAL language to follow this cycle of operation. So what I will do is I will type the same in the monitor, so we can see that I'll be just typing exactly the same thing. So I first say edit demo 1, which is the program name. Okay, so we can see very clearly that it is saying edit demo 1 is the program name, and the program starts is program is demo 1. It starts with line number 1. So first I just type in move to the point P1. Okay, then move P2, then it is approach the point P3 and keep a distance of 150. Okay, then we say open eye, then we say moves to the point P3. Okay, then we say close eye closes the gripper, then departs by a distance of 150, and then it moves to the point P4, then open eye, and then move back to the point P1. That's the cycle, and then I end it by saying end E, then ends the program. Okay, so the other we have typed in exactly what I wrote here. So it is move P1, move P2, approach P3, then open eye, then moves P3, then you close eye, then you depart 150, move P4, open eye, and then move P1 back again, and we end the program. So I have to change the speed. So let us operate at a slow speed of 20%. Okay. So now we have written the program. Now I need to execute the program. So we can, okay, I have not taught it the points P1, P2, P3, P4. Okay, because we have not entered what is the coordinates of P1, P2, P3. So I have to teach it the point P1, P2, P3. Now unlike the Swire robot, here we do not know coordinates in space. Okay, so, and it's an industrial robot. So I can use the teach pendant and take it to different positions. So I'll use the teach pendant and move the robot to different positions to teach the points P1, P2, P3. I'm teaching it. Okay, so let's say this is my point. This is my point P1. Okay, suppose this is my point P1. So what I do is I say here P1 in the code, The moment I say here P1, what it does is it gives me the coordinates. You can see the coordinates x, y, z. So there's x, y, z, and that is alpha, beta, gamma, the roll, pitch, yaw at the wrist. Okay. So if I'm happy with them, you can see that x coordinate is 513.63. Okay. So it is very difficult to get coordinates in space, and that's why the teach pendant of the map is given. Now if I'm not happy, then I change it again. Now if I'm happy with this coordinates, then I simply say enter, and now it understands that this is the point P1. Okay, that's how we teach in this case. Then I take it to another point. No, so I bring it to the point P2. So let me bring it to the point P2. Okay, that's my point P2. Okay, let me say that's my point P2, and so I'll say here P2 again gives me the coordinates, and I change it. So I've taught P1, P2. Now I have to teach it P3. Now suppose P3 is somewhere below. Okay, it's more down there. Okay, so it's down there. Let's say P3 is down there. So I'll teach it the point P3. I will say here P3, and automatically it understands that's my point P3. Okay. Now I have to teach it one more point, that is P4. So I take it, I use the teach pendant again and take it on that side. Okay, suppose that's my point. That's my point P4 now. So again, I simply say here P4, and it learns that point P4. Okay. Now I change the speed. So I've taught it the points P1, P2, P3, P4. Okay, manually I've taught it. Then I can change the speed to maybe 20%, which is slow speed. Okay, and now I can execute the program. I can say execute the program demo 1, and if I press enter, then it will start executing the program. So it will come to exactly point P1 that I taught it. Then it will go to point P2. Then it will approach. That means it will come on top of the point and wait. Then it will go down in a straight line and go back in a straight line again. Okay. Then it goes to the point P4, drops it there, and comes to the point P1. So the gripper is not active here because it's a pneumatic gripper and we require a compressor, which makes a lot of noise. So essentially what this has shown, I'll execute it again, you can see it. So I'm executing again. Something to note is the motion. So from here it is going to, I will explain it again. So correspondingly, if you see the program and what it is doing, okay, there is a 1:1 match with the program and what it is doing. So I'll run it again and then try and explain. So when this is my point P1. Okay. So first is it will go to the point P1, then it will go to the point P2. Then my point P3 was somewhere down there. So it will approach the point like this on top and then go down straight. This is my moves command, and after catching it goes back straight. So this up and down motion is always straight in straight line, okay, for safety. So you would have already also noticed that that moves command is slow when compared to the. Now let me increase the speed. Let me increase the speed to 100%. Okay, and then execute the program again. Demo 1. So this is much faster. So maybe if I want to execute it more than once, what I'll do is I'll say 5 times. Okay, it'll execute it 5 times. Okay. So if you see this motion is slow. So this is a move command, that is approach. This is the straightness, up, down, and then there. So it has executed the program 5 times, and it is saying stopped at demo 1 after executing 5 times. Okay, so there is a counter in the program which executes that many times, and then automatically it stops. Okay. Now the other features that are there are the emergency stops. All machines have emergency stops. So for example, this one and this one are emergency stops. Here also on the teach pendant we have emergency stop. So when we are operating the emergency stop, immediately the program will stop. Okay. So there are different modes by which you can operate. For example, this is the joint mode. If I press the joint mode, I can move joint by joint. So one joint is moving at a time. Okay. So you can see that one joint moves at one time. Now there is the world mode. Okay, and there is the tool mode. So if I'm on world mode, then all joints will move at the same time. So you can see that multiple joints are moving simultaneously. Okay, that is in world mode now. So depending on which mode you are operating on, there is a tool mode also, in which case I'm moving the tool mainly. Okay. So this is the world mode. And this is my tool mode. Okay, so these are different ways by which you can operate the robot. Okay.
Okay, in today's class, you saw the Swire robot programming and application of the Swire robot. You might be finding it interesting in the sense that this is a robot where you can catch it and move it around, and it is safe. So this is the next generation of robotics, what we call as collaborative robotics. The other was the Puma robot, which is an industrial robot, and it is strictly an industrial robot in the sense that it is not safe. So there is normally, human beings are not supposed to be standing near a robot when it is operating, because it can be very, very dangerous. So today we stop here. Thank you.